Assalamualaikum. This is Nusrat Jahan and I am from the Department of Computer Science and Engineering at Kumbh University. I am bearing ID 12308039. Today I will be presenting a fundamental topic in digital electronics named clocked RS and JK flip-flops. They are essential components used in memory, counters and sequential logic systems. In this presentation, we will understand what flip-flops are, how RS and JK types function, their differences, and where they are used in real-world applications. Now, before diving into specific types of flip-flops like RS or JK, we first need to understand what a flip-flop is at its core. A flip-flop is the most fundamental memory element in digital electronics. It is a bistable device, meaning it has two stable states, logic 0 and logic 1. Once it is in a state, it stays there until an input forces it to switch to the other state. In other words, it can remember one bit of information, either 0 or 1. These characteristics makes flip-flops the building blocks of memory, counters, and sequential digital circuits. Now, understanding the truth table of the basic diagram of a flip-flop, here we see the set condition when S equal to 1 and R equal to 0, the output Q becomes 1 and Q prime becomes 0. So the flip-flop is now set, storing a logic high value. Then the second condition, reset condition, when S equal to 0 and R equal to 1, Q becomes 0, Q prime becomes 1. So the flip-flops is now reset, storing a logic low value. Next, the hold condition, when S equal to 0 and R equal to 0, the outputs remain unchanged. This is now known as the memory or stable state. The flip-flops remembers the previous value. When the invalid condition, the S equal to 1 and the R equal to 1, both outputs becomes 0 temporarily, which is logically consistent since as Q and Q prime always be complements. This causes a rest condition and the result will be unpredictable. Now let's talk about the clocked RS flip-flop. RS stands for reset and set. This flip-flop only changes its state when there is a clock pulse, making it age triggered. It has three inputs: S for set, R for reset, and clock. The output is represented by Q and its complement is Q prime. The basic operation is simple. If set is active, the output goes to 1. If reset is active, the output becomes 0. However, the output only responds when a clock signal is applied. Now, we will understand the logic diagram of RS flip-flop. Before understanding the logic diagram, we have to know the components. The circuit includes two AND gates, one basic NOR-based RS latch. The inputs to this flip-flop are, first of all, set to set the output to 1, R for reset to reset the output to 0, clock which controls when the flip-flop can change state. The outputs are Q, the main in output, and Q prime, the complement of Q. Now, how it works, we can understand step by step. The role of the clock. This flip-flop does not react to the S and R inputs directly. Instead, the S and R inputs are gated through two AND gates, each of which is also connected to the clock signal. This means that only when the clock signal is high, this means when clock is equal to 1, the values of R and S are allowed to pass through the AND gates and reach the NOR latch. AND gate operation. When AND gates takes S and clock as input, it shows the result to the set input of the latch. Then when the other AND gate takes R and clock and connects to the reset input to the latch. When clock equal to 0, both AND gates are disabled. The outputs of the AND gates are 0. Therefore, no change occurs at the NOR latch. The output holds its state. Then when clock equal to 1, the values of S and R passes through. If S equal to 1 and R equal to 0, the flip-flop sets Q equal to 1. S equal to 0, R equal to 1, flip-flop resets Q equal to 0. When S equal to R equal to 0, it remain hold state. When S equal to R equal to 1, it remain invalid state, just like the basic RS latch. Let's now go through a practical example of how the clocked RS flip-flop works in a real situation. We are told that the initial output Q is 0, so its complement Q prime is 1. Now we apply a clock pulse and set S equal to 0, R equal to 0. So the clock is active when the inputs are processed through the AND gates and then passed to the NOR latch. First of all, R equal to 0 and clock pulse is 1. So 0 and 1 equal to 0, which remains in function of f. Then clock pulse equal to 1 and S equal to 0. So 1 and 0 equal to 0, which remains in f prime. Then when Q equal to 0 and f prime equal to 0, so 0 NOR 0 equal to 1, which remains in Q prime. Then 1 Q prime equal to 1 and function of f equal to 0. So 1 NOR 0 equal to 0, which remains in the actual Q's value. One major issue with RS flip-flop is race condition. This happens when both S and R are 1 while the clock is high. In this case, both outputs Q and Q prime could temporarily become 0 or 1, breaking the rule that Q and Q prime must always be opposites. Now we understand what is happening. If we see the first diagram, R, S and clock pulse are 1, even the Q and Q prime are not complement. This means Q and Q prime are 0, but this is not an invalid position. But when we take the second diagram, we see that R and S are 1, but clock pulse is low, that means CP is 0. So the input of the NOR gates are 0 and output of the NOR gates are also 0. So this is an invalid position. So we have to remove this. So if we take Q at first, this will 0 NOR 0 will be 1, which remains in Q prime, and 1 NOR 0 will be 0, which remains in Q. Even if we take Q prime at first, so Q prime is 0, 0 NOR 0 will be 1, which remains in Q, and 1 NOR 0 will be 0, which remains in Q prime. This is the main problem. If we take Q at first, this will Q equal to 0 and Q prime equal to 1. But when we take Q prime at first, Q equal to 1 and Q prime equal to 0. So both become Q and Q prime 1 or 0 temporarily, which oscillating the diagram. Let's talk about the excitation table. The excitation table tells us what inputs S and R we must apply to the flip-flop in order to achieve a desired transition from the current state Q to the next state Qt plus 1. This is basically the reverse of the truth table. Here's how to interpret it. Let's go through each row. In row 1, if the current state is 0 and we want to stay at 0, then we apply s equal to 0 and r can be anything denoted x, meaning don't care. In r equal to 2, to go from 0 to 1, we must set the flip-flop so s equal to 1 and r equal to 0. In row 3, to go from 1 to 0, we must reset the flip-flop so s equal to 0, r equal to 1. In row 4, if the current state is 1 and we want to stay at 1, then r equal to 0 and s can be anything, that means don't care position. This table is useful when designing logic circuits because it tells us what inputs are needed to get desired state transition. Now talk about characteristic equation. A characteristic equation of a flip-flop gives us a Boolean expression to calculate the next state qt plus 1 based on the current inputs and current output qt. Now let's derive the equation. When is qt plus 1 equal to 1? Row 2, qt equal to 0 to qt plus 1 equal to 1, s equal to 1, so r equal to 0. In row 4, q2 equal to 1 to qt plus 1 equal to 1, so r equal to 0 and s equal to don't care position. So the next state qt plus 1 becomes 1 in two cases, when s equal to 1 regardless of q, when r equal to 0 and q equal to 1. So qt plus 1 equal to s plus r prime q. This reads qt plus 1 is 1 if s is 1 or if reset is not active and current q is 1. When q is qt plus 1 equal to 0, row 1 q equal to 0 stays 0, so s equal to 0, r3 q equal to 1 becomes 0, r equal to 1. In both cases, either reset is active, this means r is 1, or set is 0 and no active change happens. So logically the condition for the output becoming 1, qt plus 1 equal to 1 is captured by qt plus 1 equal to s plus r prime q. In the right corner we see a graphical symbol of RS flip-flop. Now we see that the standard truth table for RS flip-flop when a clock pulse is present. When both S and R are 0, the state is held and this remains unchanged. When S is 1 and R is 0, Q becomes 1, so this is set. Then Q becomes 0 when S is 0 and R is 1. This becomes reset. But if both S and R are 1, the output becomes invalid. This means the race condition. This limitation is one of the reasons for developing the JK flip-flop, which we will discuss next. Now we shift to the JK flip-flop. The JK flip-flop is an improvement over the RS flip-flop. It has the same basic functionality, set, reset and clock, but eliminates the invalid state. Instead of S and R, the inputs are labeled as J and K. When both J and K are 1, the flip-flop toggles, meaning if the output was 0, it becomes 1 and vice versa. This toggling is very useful in counters and sequential circuits. Here we see the logic diagram of JK flip-flop and characteristic table. The JK flip-flop logic diagram looks more complex because it includes additional feedback paths that prevent the invalid state found in RS flip-flops. It uses NAND gates and control feedback to ensure that outputs always remain valid even when both inputs are high. In the RS flip-flop, we see that when S equal to 1 and R equal to 1, in both the position of Q 0 and 1, it becomes invalid. But in this logic diagram, we see that in both position qt plus 1, that means the next state becomes valid. Let's talk about this in the next slide. Let's go through an example. Suppose q equal to 0 and q prime equal to 1 initially. If both j and k are 0 when the clock pulse occurs, the state remains unchanged. That means when r equal to 0, clock pulse equal to 0 and q equal to 0, so 0, 0 and 1 will be 0, remains in function of f. In the next s equal to 0, q prime equal to 1 and clock pulse is 1, so 1, 0 and 1 will be 0 in AND gates, which remains in f prime. In the NOR gates, q equal to 0, so 0 and 0 for the NOR gates will be 1, which remains in q prime. From the q prime of 1, 1 NOR 0 will be 0, which remains in the next state qt plus 1. We talk about the main flip-flop. When S and R both are 1, even clock pulse is high, that means CP is 1. Q equal to 0, so Q prime will be 1. So 1, 1 and 0 in the AND gate, the result will be 0, which remains in F. Then S equal to 1, clock pulse equal to 1, even q prime equal to 1, so 1, 1 and 1 in AND gates, this will result 1, which remains in f prime. Now we take q equal to 0 and f prime equal to 1, so 0 nor 1 equal to 0, and we take q prime equal to 0 and f equal to 0, so 0 nor 0 equal to 1, which remains in the next state qt plus 1, which is the main. Let's talk about the excitation table. Here we see that when the current state is 0 and we remain at 0, so the input of j is 0, but k can be anything, so k is x, which means don't care. When the current state is 0 and the next state is 1, j is 1 and k can be anything, that means don't care position. When the current state is 1 and the next state is 0, that will be j can be anything and k is 0, sorry, k is 1. And when q and qt plus 1, that means current state and the next state both are 1, if j can be anything and k is 0. Next, the characteristic equation of the j-k flip-flop. Qt plus 1 equal to j dot q prime plus k prime dot q. The equation tells us the next value of q using current input values j, k and the current state q. Let's break it down turn by turn. Qt plus 1 is the next state of the flip-flop what we want to calculate. Q is the current state either 0 or 1. Q prime is the complement of 0, opposite of q. J is the set input like as is in RS flip-flop, and K is the reset input, and K prime is the complement of gray. Now let's interpret what each part of the equation means. When Qt plus 1 equal to J dot Q prime plus K prime dot Q, the first prime J dot Q prime, this part becomes 1 when J equal to 1 as is active and Q prime equal to 1 as, which means q equal to 0. In other words, it sets q to 0 to 1 when q was previously 0 and j is active. Second term k prime dot q, this part becomes 1 when k equal to 0, so k prime equal to 1, no reset, and q equal to 1 flip-flop already set, so this holds the value of q as 1 when we do not apply reset. Combining both terms, The flip-flop sets Q to 1 if J equal to 1 and Q as 0 toggle up. It holds Q as 1 if it was already 1 and reset is not active. Combining both terms, we said that if J and K are both 1, it toggles. Q becomes Q prime. If both J and K are 0, it holds the current state. The characteristic equation Qt plus 1, we found that J dot Q prime and K prime dot Q models all these conditions perfectly. This is the truth table of JK flip-flops. When both J and K are 0, the output holds its states. If J is 1 and K is 0, the flip-flop sets. If J is 0 and K is 1, it resets. And if both are 1, it toggles. This toggle pacer makes JK flip-flops suitable for many real-time digital operations like binary counters. We see the basic differences of RS and JK flip-flops, as the design of RS flip-flop is simpler and JK flip-flop is slightly more complex. Even there are invalid position in RS flip-flop, but JK flip-flop has no invalid state. And when the flip-flop of RS is invalid, the position of S and R equal to 1, but there are available J and K equal to 1 in the JK flip-flops. This is the slightly differences of RS and JK flip-flop. The in the applications, RS flip-flop are used in basic memory elements and control systems where simplicity is important. JK flip-flops, because of their reliability and toggle function, are commonly used in counters, sequences, generators, and shift registers. Their ability to avoid invalid states makes them ideal for more complex and suitable design. That's all from me to understand the basic idea of RS flip-flop and JK flip-flop. Thank you for your attention.